class now?
Yes. I still see a couple of students connected online. Again, attendance is not going to be counted there, but at least they'll get the information.
Oh, so you're still streaming?
Yeah, because I want to record the videos. I think it's helpful to have the videos recorded. What if you want to watch the lecture on Saturday because you're bored?
Record it without streaming.
Eh?
Well, you can still record it without streaming, can't you?
But then I have to use another software. It's easier just to have it on Blackboard, just using the same thing. Right?
I thought you were completely closing it.
Again, I mean, I don't care. The point is that it's not working for them.
Right.
That's, if they want to keep doing it, then that's on them. But, it doesn't really affect me.
Right.
I'm fine. Okay, so what was your question, Franklin?
So on 5.1, question 5, I can see info they're providing. I'm just trying to figure out the relation between it, I suppose.
So hold on a second. Okay, so we're seeing this. So you told me it was a question that was asked in the forum?
No, I've been forgetting to ask it on the forum.
Okay, so
That's my own fault.
it's 5.1 or before?
5.1.
5.1, what problem?
Question 5.
Question 5.
They're presenting us a few facts, such as certain sequences equal this, and then they're asking,
This one?
no.
That's
I just
question
checked
5.
on the I just checked it on the laptop. Did it change then?
It shouldn't.
I don't think everybody has the same question as it.
Yeah, it's not the same question.
Yeah,
So
but
it's a question where the sequence of C1, C2, C3 equal K, e to the C1, e to the
Oh,
C2.
but no, that's not question 5. That's
15. I got it.
Yeah, I remember that one.
Yeah,
Question 5.
really?
Yeah.
For example, it shows up here as question 8. You mean this one? Something like this?
not quite that one.
Oh, but it's like this one.
Similar,
Okay.
but the final equation they're asking is, I think C to the N over C?
It's gonna be n raised to the power of 3 over n.
Oh,
It's similar to that.
I saw
one,
I saw a question. I know what you're talking about. Is this randomizing the problems? I don't want it to randomize.
I think
I mean, the values will be randomized, but the order of the question should not be changed.
yeah, I don't see it on there.
Yeah, I know exactly which one you say. I know there is this one. There should be another one.
Maybe if you submit that question and then like jump to a different form.
No, that's fine. That's fine. I'm just gonna enter in yours. Do you mind if your information shows up?
That should be fine.
Okay.
Pretty sure.
Where is Franklin? What's your last name?
LLANES.
Ah, Janis.
Be on there.
5.1.
5.1.
So this is your question 5.
It was under question 5 for me.
This is your question 5.
Okay, the one I was having trouble with, I think, might have been 7 or 8. If we can glance down there real quick. Yes.
Okay, 8.
Here.
Yeah, I think it's one of those because I have some questions here that they are blocked and then it randomly selects like 2 out of 5. And then it could be that instead of picking the one that you saw for me, pick this one for you. But it's the same type of question. This is undeterminate form. So basically, it's just telling you, so if you have a sequence has limit k, then this sequence has limit e to the k. So, that's because exponential is a continuous function.
Yeah.
So, if you do e to the power of this sequence, whatever this sequence approaches to, this is a new sequence. E to the C1, E to the C2 is a new sequence. The limit of this sequence is going to be e to the power of whatever this limit is.
Right.
That's all this is there telling you. So they say use this fact together with nominal rules to compute the limit sequence given by this. So the point is that when you take this limit, right, this is going to be, remember, this is an infinity. This is infinity to a 0. So this is an indeterminate form. how you deal with infinity to the 0, you write it as e to the ln, bring it down, and then you solve the rule and all of that business. And that's where the e comes from, and then the point is that because e is continuous, this is going to be e to the power of whatever the limit of the stuff from the top you get.
Yeah, I was thinking completely right.
Do
Okay,
you-
that's where we're getting.
So do you need me to do it, or do you think that
I'll try again, and if not, I will remember to actually ask on the forum this time.
okay.
And
So-
we're gonna give it one more college try first.
Yeah, so let's see. I'm just gonna get you started so you can see what I mean. So n to the 5 over n. So you have bn is a sequence n to the 5 over n. So first of all, because I know I'm gonna be using L'Hopital rule and so on, I'm gonna go to the function. Okay, so we're gonna be considering the function x to the 5 over x. Okay, just so we can take derivative and all of that. So if we take the limit as x approaches infinity of the function, what do we get? So it's going to be infinity to the 0th power, so this is an indeterminate form. Remember the strategy. When you have infinity to the 0, what do? We write it as e to the ln, so that we can bring the 0 to the front. And now this right here is a 0 times infinity situation. Okay? And what we're going to do is, to compute this limit, we're going to do this trick, and then we compute the limit in the top, and then, because the fact that the homework says, and also what you know about continuity, the result is going to be e to the power of whatever this limit is. That's what that first sentence is there to hint to you that you should be doing this kind of process. Okay? So, we have this, so this is the limit as x approaches infinity of e to the ln x to the 5 over x. Now bring it down. Okay, and then finally this is e to the limit. You can pass the limit through and then just focus here. Now if you don't mind, I will already write it like this because it's easier. Now instead of having a 0 times infinity, we already have an infinity over infinity, so we can do L'Hopital rule right there. Okay. All right. So that's basically what's going on. In fact, you can do L'Hopital rule if you want, but you can use the growth of the functions. This is a line, that's a logarithm. This is one of the slowest functions that you have around. So this one grows faster, so this limit would be 0. You can do L'Hopital rule, you will get 1 over x, this is 1. So basically you're going to get 5 over x, so you're going to end up with 0. E to the 0, so this is 0, so the answer would be e to the 0, which is 1.
So,
Right?
okay.
So that means that Bn approaches 1.
Yeah,
Okay?
yeah, I completely liked on actually turning the exponent into a 0 and then making it ln infinity into 0.
Remember, because I saw this in the exam, you guys seem to have issues with indeterminate forms. Every time that you take a limit, you have to first plug in and see what you get. Okay? You have to plug in. If you plug it in, there are 7 expressions that if they show up, it's indeterminate. You need to do something about it. And this is one of them. You plug in and you get infinity here and 0 here. That's infinity to the 0. This is indeterminate form. And there are tricks for this, as you can see. Right? Techniques to deal with that.
That's a good refresher.
Okay. So remember, I maybe 3 lectures ago or something like that, I gave a summary of all of this, how to deal with
And I forgot it.
with each of them. All right, good.
Thank you very much.
Okay, so that was that. It's a good question. Again, maybe not all of you have the same question because, as you can see, for me, another question pop up instead of this one. But it's the same idea. That the question that was showing up for me was a 1 to the infinity situation, which again, you deal with it the same way. Okay, this technique that we use is used for infinity to the 0, 1 to the infinity, and 0 to the 0. These 3 forms, this is how you solve. Okay, you write as e to the ln to bring the power down. So, okay. All right. Any other questions about sequences? We good? Okay. So now what I want to do is let's finally begin with series, and let's see what we can do today. So the idea here is to discuss the notion of infinite series, make sure that we understand what they are and how we handle them. So what do we do to be able to understand infinite series? And to motivate this, I want you to look at this little problem. Okay. So consider a square of psi 1. So you have a square of psi 1, and then we're going to play the following game. You're going to split it in 4, and you're going to change the quarter of the square. Right? So the first step looks like this. Everybody okay with this? 4 equal pieces, you shade this. Then you're going to pick one of the empty squares and repeat the process. Yes? And so on. So step 2 will look like this one. And then pick one of the empty squares. I don't know, let's keep picking the corner guy. And then you continue this process. Okay? The question is, okay, at this point you're going to have infinite. Do you understand that there will be infinitely many little squares shaded in this process? I would like to know the area. Okay, what's the shaded area after we do this process? That's a question that we want to answer. And the whole point is that our discussion today will be to try to make sense, model the situation, and try to make sense of it, and eventually give an answer. Okay, that's what we want to do. And this is going to motivate the notion of an infinite sum, because as you can see, to calculate the area, you're actually calculating an infinite sum, right? You're adding infinitely many numbers, the area of those infinitely many little squares. Moreover, they are all positive. So you're adding infinitely many positive numbers. So the question is it possible for a sum of infinitely many positive numbers to be a finite number? What do you think?
I mean, looking at the geometry, yes,
Why?
because we already have a limited area. But
What do you mean by a limited area?
we've been presented with a sphere that sizes are exactly 1 by 1.
Uh-huh.
So we cannot get to, and we shouldn't be able to get to an area that is a total area that's bigger than 1.
Very good, right? So right here you have a square of psi 1, so you know that the maximum area here is 1. And whatever we have here is going to be a number that's less than 1 actually, because there are a bunch of squares that we're not filling in. If you think of this as being a sequence, what's happening to the area? Imagine that the first term of the sequence is this area. The second term is the sum of these two areas. The third term is the sum of the three areas, and so on. So that will be a sequence, right? As you go deeper into a sequence, what happens to a sequence? It's getting bigger and bigger, right? Because you're adding a tiny little area. So it's an increase, it's monotonic increase. But what do you know about this sequence? It's bounded, because that sum will never be more than 1. What did we discuss last time? Monotonic and bounded must converge. So there is a number to be found. Okay, our job now is to try to find that number. Okay, good. All right, so let's see. Let's formalize this then. So we have this process, and then the question that we want to ask is find the shaded area. Okay, so there will be several things that are going to come out of this. So let's start modeling this little by little. Okay, so let's suppose, so let an, so we're going to be doing this process for indefinitely, right? So I'm going to call A1 the area of the first square that we check. A2 is going to be the area of the second square that we check, and so on. So AN is the area of the nth square, okay? And our job first is to figure out a formula for AN. That's what I want. I want to figure out a formula for AN. So let AN be the area of the nth shaded square. So to find a formula for AN, we need to know the dimensions of that little square, and then we can use the formula. So let's start doing this little by little, and then hopefully we're gonna figure out the part. So let's see. To compute A1, what do we do? Initially, you have a square of psi 1. Right? Everything is 1 here. Then what we do is we split it to 4 equal pieces, and then we shade 1. What are the sizes of the square that we're shading? Right? So this is 1/2, 1/2, right? 1/2 by 1/2. Everybody okay?
Yes.
because that's what we are changing. So what is the area? Was A1 equal to? Okay, 1/2 squared.
Okay.
Remember, we're after a pattern, so you have to look for the pattern. Okay, you can put 1/4, but I'm gonna put 1/2 squared. Then if we need it, we're gonna put the 1/4. Okay. All right. Let's take a look at A2. What would be A2? So we have to take now a square size 1/2, right? We take a square size 1/2. Let me do this. We split it into 4, and we change one of the little squares. What's the size? What's the new size? What's the size of the shaded square? 1/4, right? So what's the area? 1/4 square. Everybody okay with this? I'm gonna do one more. A3. What would be A3?
1/4.
So you have 1/4, right? What do? Split it, and then consider this. What's the dimension of the shaded?
1/8.
1/8. So it would be 1/8 squared. Can you predict what will be the next one? Let's see. Without me drawing a picture, tell me what's A4. 1/16 squared. Good. Does everyone understand this? So you need to have the dimension of the square every single time, right? As we go to the next step. Let's see if we see a pattern here. Do you see a pattern? So what's a pattern?
This divided by 2 and squared.
Yeah, but let's try to figure out a formula. So what's AN, right? So, for example, notice that all of these guys are powers of 2, right? So that's 2 to the 1, the denominator, look at the denominator. 2 to the 1, this is 2 squared, this is 2 cubed, it's 2 to the 4. So the next one would be a 32, which is a 2 to the 5, right? So on. But then that's being squared, so how can we write that?
1/4 to the n.
1 over 2n.
So we can write this as 1 over C.
No, because then.
It's probably more comfortable to go to the 4, you see?
So it'd be 1/2 to the n plus 1.
Let's see, I'm gonna play with this a little bit, okay? So I'm gonna write this as 1 to the 4. I think it's more comfortable to leave as 1 to the 4. Then this one will be 1 to the 4 squared. Now this one, I would like it to be 1 to the 4th cube. Let's see if we can make it so. So this is 1/2 cube squared, right? Because 2 times 2 times 2 is 8, right? And then you square it. And remember, because when you do the exponential of an exponential, you multiply, and you could do 3 times 2, but you can also do 2 times 3. In other words, I can switch these two guys, right? So I can switch, but then 1/2 squared is 1/4. So this is 1/4 squared, and 1/4 cubed. Sorry. Okay. So square, cube. Let's see. I'm expecting to get 1/4 to the 4, right? And indeed, this is 2 to the 4, right? Then the 2 and the 4 we can switch. Basically, what we did was this is 2 to the 3. The 2 and 3 were switched, right? That's 2 to the 4. So the 2 and 4 are switched. So I can write this as 1 over 2 to the 4 square, which I can switch it as 1/2 squared to the 4, which is a 1/4 to the 4. I don't know, this is nicer because the index here, you can think of this as to the first power. The index of this matches the power. You see that? So it's always 1/4 raised to whatever the index is, right? So according to this pattern, let's see, the first one that we figured out was AN. What did we figure out it was supposed to be? Okay, that's the last one that we figured out. We're expecting this. But the original one, what was it? This is 2 to the 4, right? Square, so this should be 2 to the n squared. Right? That was the original one that we figured out. And I want to see it like this. So can we see it like that? Yes, it's exactly the same thing. Just switch, and then you get that. Okay? So moral of the story, the area of the nth square is given by 1/4 to the n. Do you understand this?
Yeah.
So that's the area of the little square, okay? Whichever little square you want. And the point is that you keep on doing this process over and over again. So the question that we are interested, the area that we want, is equal to what? How do we calculate this? A1 plus A2 plus A3 and so on. Exactly. It doesn't stop. Do you understand this? So the area that we are interested in can be written as quarter plus a quarter square plus a quarter cube. Keep going. Typically, when we have this kind of stuff, we like to write the nth term if we have it. But then it's very important to write these 3 dots at the end. This is saying that this keeps on going non-stop. Okay? All right. So let me introduce to you a notation for this. We have not used, well, you have seen my notation already when you talk about integrals at the beginning, Riemann sums, and all of that business. So we can rewrite this as the sum. Let's see, my index begins at 1, so I can say n going from 1 to infinity of an. So this is just something formal. This is just a shorthand way of writing that. Do you understand this? So what this means is, first of all, I'm doing a sum. This would be an infinite sum. And what am I adding? What am I summands? Well, n equals 1 is an a1, whatever this is. Okay? a1 plus a2, because this is like a counter. This is growing 1, 2, 3, 4, 5, non-stop. If I put a 20 here, then it will be from 1 to 20, so it stops at 20. Okay? And whatever this is, you just plug it in here. So if I put a 20, this would be a1 plus a2 plus a3 plus a4 all the way up to a20. Okay? Because it doesn't stop, then that's why you see an infinity. Following the same idea, let's rewrite it now with this expression. How would it look like? This summation? What is it? That would be the sum from 1 to infinity of 1/4 to the n. Okay? This is just a shorthand way of writing this infinite sum that we have here. Okay? When n is 1, you get a quarter. Plus, when n is 2, you get a quarter squared. And so on and so forth. Yes? Okay. We want to make sense of this. So, by the way, we know that this is going to be something, right? Because let's make sense of that. Why? Because notice that how was it that we came up to the conclusion that this was going to be something? Even though this is an infinite sum, we were looking at it as a finite sum. Because this finite sum was getting bigger and bigger and bigger by adding a term, right? So we're looking, I told you to consider the first term of the sequence is the first guy. The second term is the sum of the first two. The third term is a1 plus a2 plus a3, and so on, right? As you go deeper into the sequence, you're getting closer and closer to this infinite sum. That sequence that I mentioned is called the sequence of partial sums, okay? And that's what we use to be able to understand infinite sums. We analyze the sequence of partial sum. If that sequence converges, then we would say that this infinite sum converges. And it's equal to whatever that number is, okay? Anyways, I'm gonna write all of that down now. So let's try to make sense of this. So the point is that this is now an infinite sum, okay? And notice that this infinite sum, how did it come to be? We first came up with a sequence. What sequence do we have? We have the sequence of the little areas, A1, A2, A3, that's a sequence. And what did we do? We decided to add them. So when you add the terms of a sequence, what you get is a series, okay? A series is just a result of taking a sequence and adding up all these terms. That's all it is. All right, so definition. So suppose that you have an infinite sequence. So let an be an infinite sequence. Then the sum of its terms is called an infinite series. Then the sum of all its terms, and let's say the sequence begins at 1, but again, it could begin at 0 as well, okay? So a1 plus a2 plus A3, etc. The shorthand notation for this is from 1 to infinity of an. If for some reason we have our index beginning at 0, then you just put from n equals 0. Okay, that's very typical. So the sum of all its terms is called an infinite series. Our task now is to make sense of this and being able to understand what it means for something like this to equal a finite number, if it equals a finite number at all. Okay? And the effort, our entire effort that we're going to have in this entire chapter is having a series, how can we determine whether it equals a number or not. What you're going to learn is that actually in very special cases, you're going to be able to figure out exactly what this infinite sum will be equal to. The most that you will be able to say is whether it equals to a number or not, so whether it converges or diverges, okay? But in some special cases, we will be able to precisely compute this, okay? But most of the time, you will just have to, you need to content yourself in saying whether it converges or not. And then there are theorems that allow you to approximate those values that it may converge to, okay? And we're gonna discuss some of those in some special cases. Okay, so an infinite series, what is it? It's just, you have a sequence, you add up all the terms, and then what you get is called an infinite series. Now, there are some terminology here. These terms, A1, A2, A3, they are called the terms of the series, okay? And AN, whenever it's provided, this is called the general term of the series, because you have a little formula that you can play with, okay? This is called the general term of the series, so let me write that down. So I guess first let me write a remark. Sometimes we begin with 0. Okay, we begin with n equals 0. It really depends how you want to write your part. Okay, so sometimes we begin with n equals 0. So it will look like this: the sum from 0 to infinity of an. Doesn't really make too much of a difference. It's just one term, right? You have an a0 in there. And usually when the starting point is understood, or if it doesn't really matter, we just don't write this and we just write the sigma notation with the an, and we skip this right here. Okay, so when it doesn't matter, or if it's understood where we begin, then we skip this. So usually when it is understood or not important, the beginning index, we write, yeah. So you may see me writing these a lot, because just so I don't have to be writing from here to here, or whatever. As long as it is understood what we're doing, okay? And you can see that in many places as well, so just keep that in mind. Okay, so the terms A1, A2, A3, etc. are called terms of the series. And an is called the nth term of the series. Okay, so now that we have those names in place, then the question is, how do we make sense of this? How do we make sense of an infinite sum? So a natural question is, okay, that's fine. We already know that this makes sense because of the example that we started with. Because right here we have an infinite sum, and we know this better equals something, okay? Because it's not gonna be something bigger than 1. So it has to equal something. It cannot just go to infinity. All right, so how do we make sense of this? Infinite sum. Basically, we're gonna use the same idea that we use for improper integrals. So remember, how did we make sense of improper integrals? What was the idea? of type 1. So we had an interval from, let's say, from 1 to infinity, right? And the problem is that because it's not from A to B, then we couldn't use fundamental theorem of calculus really. So what did we say? Well, let's cut at some point. So let's make the interval finite. So instead of looking at the infinite interval, let's look at a finite interval. We know what to do there because we have techniques, right? We have fundamental theorem of calculus, etc. And then we took a limit to make this finite interval closer and closer to an infinite interval, right? By taking the limit, we make it infinite. Yes? So we're gonna do the same thing. If you want to understand an infinite sum, what do? Well, we know how to add finite remaining numbers, so we cut the sum at some point, and we add those finite remaining numbers, and then as you start getting closer and closer, adding more and more numbers, you get closer and closer to the behavior of the actual series. So you cut at some point, that's called the partial sum. I'm just going to take the limit as an approaching thing. Exactly the same thing that we did for improbability. Okay? So you try to study what you don't know with stuff that you know. That's the idea. You know how to deal with finite sums, so let's use that technique to understand infinite sum. Okay? So that means that when you have a series, there are two sequences attached to it. The first one is the one that you use to make up the series, the AN. Okay? Then there is another sequence that you're going to produce, which is called the sequence of partial sums, which the first term is A1, the second term is A1 plus A2, the third term is A1 plus A2 plus A3. Okay? And so on. So you're partially adding the terms of the series, little by little, as you go deeper into a series. All right, so let me write that down. And that's the one that we studied. So, idea, every series have a sequence as follows. So you have a series, I'm just gonna do it from 1 to infinity, okay? You have a series from 1 to infinity AN. So remember, this is A1 plus A2 plus A3 plus A4, etc. So what we're gonna do is the following. So let Sn be a sequence defined by the following. So S1 is going to be equal to A1. S2 is going to be A1 plus A2. So this is your S1, then this will be your S2, and so on. Okay? S3 is A1 plus A2 plus A3. We keep going this way, then Sn is given by the sum of the first n terms. But if you want, you can use the sigma notation. That would be the sum from k going from 1 to n of ak. Okay? Basically, you call it at n. Instead of going to infinity, you're just calling the sum at the nth place. Okay? So that sequence is called the sequence of partial sum. So this sequence is called the sequence of partial sums. And it should be clear why it's called like that, because you're partially adding the terms of the series, little by little. Okay? It's called the sequence of partial sums and of the series AN. Okay? So you can define Sn in Word as the sum of the first n terms of the series. Okay? But you need to keep in mind that if the series begins at 0, it's really the sum of the first n plus 1 terms of the series. Okay? Because if it begins at 0, you call it n, but you have an A0, A1, so you have n plus 1 terms. Okay? So depending, if it begins at 1, it's the sum of the first n terms. If it begins at 0, it's the sum of the first n plus 1 terms. So always, keep an eye on what the starting index. And it's clear that as n gets bigger and bigger, the value of Sn is getting closer and closer to whatever the series is, right? Because the bigger this n is, the more terms you're adding, so the closer you are to that infinite sum. So it makes sense that if you want to study what this infinite sum equals to, you should be taking the limit of this as n approaches infinity. Yes. So as a definition. So we're gonna set. So we have this, and note as n gets larger and larger, Sn gets closer and closer to the behavior of the actual series. Okay, so we basically set that the series we set it to be equal to the limit as n approaches infinity of Sn. That's the idea. I'm going to now formally write that down, but that's basically what it is. When you want to analyze a series, you have to look at the sequence of partial sum and study that. And if that sequence converges, then that means it has a limit, it equals to something, then the series will converge and it will equal to that limit. Okay? If this sequence diverges, then the series diverges. It doesn't equal anything. Okay? If you're adding all these terms, divergence means it will go to infinity. All right. So definition. This is the definition of convergent or divergent series. Okay. So for an infinite series, an is sum from 1 to infinity. An, the nth partial sum, the nth partial sum is Sn, that's what we just defined. A1 plus A2 all the way up to An. And then if the sequence of partial sum converges, then the series converges. Otherwise, the series diverges. So if the sequence of partial sums, so you have this sequence Sn, okay? So if this sequence converges, then the series converges. Okay. The limit as n approaches infinity of Sn. So if Sn converges, has a limit, we call it S, and this number is called the sum of the series. So we set the series equal to this number. Okay, is the sum of the series. So a limit is the sum of the series, and then you write the sum from 1 to infinity of An equals S. Okay. Now, if the sequence of partial sum diverges, then the series diverges. Okay. So if Sn diverges, then the series diverges. Okay. So that's the point. So that's how we understand infinite sums. So we basically translate the question to a finite sum, study that finite sum. And when I say study, I mean you look at the sequence of partial sum, try to figure out whether it converges or not, and then the convergence of that sequence tells you what happens to your series. Okay? So that's why we needed to spend some time talking about sequences, because as you can see, the series is, to analyze a series, you will actually go back to looking at a sequence. Okay? All right, so let's do an example. I'm going to introduce an important series. It's called the harmonic series. Okay? So the harmonic series. This shows up in many places, like even in music. I don't know how, what happens there, but it has to do with in music. Probably that's the reason why it's called harmonic. Okay, this is a series 1 over n. So the harmonic series is a series obtained by looking at the sequence 1 over n. Okay, so that would be the sum from 1 to infinity of 1 over n. So this is 1 plus 1/2 plus 1/3 plus 1/4 and so on. So this is called the harmonic series, and we're gonna try to see whether this series converges or diverges. Okay, we're gonna see what happens here. In the next section, we're gonna study the integral test, and then we're gonna have another way of easily seeing whether this series converges or not. Okay, but right now we're gonna do it with elementary means. In other words, just by the definition. Okay, the point is that you're gonna see very quickly that the definition is nice, but it's also very hard to work with, because it means that you need to understand this finite sum, but 1 plus 1/2 all the way up to 1 over n. How do you study that sequence? You need to have some clever ways of dealing with it, okay? So that's why we're gonna try to develop some tests and some theories that will allow us to test for convergence without having to go directly to the sequence of partial sum, okay? But that's happening in the following sections. Right now, this is what we have, so this is what we're going to work with. Okay, so if we want to understand what happens here, so I'm not telling you whether it converges or diverges yet. So we're going to try to investigate, okay? So if we want to understand what happens, we need to understand Sn, okay? So let's see. Consider Sn. And what is Sn equal to? Is 1 plus 1/2 plus 1/3 plus 1/4. Let's see, there is a reason why I'm writing a bunch here, okay? So I'm gonna do it up to 1 over 8, and then all the way up to 1 over n. Okay, so let's see, in particular, I want to go all the way up to, okay, this is Sn. Let's take a look at a subsequence. Let's say that the n that I pick is a power of 2. So I want you, okay, you're gonna see why I'm doing that pretty soon. Let's see, this is equal to 1, right? Now here is what I'm gonna do. I have a 1/2. Let me put 1 plus 1/2. Now, what I want to do is I want to start building a bunch of 1/2 in here, okay? And how can I do that? For example, here I have a 1/3 plus a 1/4. If I replace this 3 by 4, I'm going to get a 1/2 when I add these 2, right? But what happens if I replace this 3 by 4? Do I get something bigger or smaller?
Smaller.
Small, yes, smaller, right? Because if you put a 4 here, you're going to have, yes, a smaller number. So, yes, if you divide by something bigger, the fraction gets smaller, right? So if I replace this by a 1/4, then I'm going to get something smaller. So this equal sign is going to turn into a greater than or equal to, right? Because instead of that 1 over 3, I'm going to put a 1/4, and then I have another 1/4. Yes? So basically what I did was, I changed this 3, I changed it for a 4. So I made my sum smaller so far. I mean, this is going to keep going, okay? It's going to keep going. Yes?
So that long sequence you wrote, that's going to be on the left side of the greater than or equal to sign, right? So like
Yeah,
what
yeah.
you're doing is kind of what we did Tuesday.
Yeah, this top is greater than or equal than.
Okay.
Well, of course, I'm not done writing. So
right.
if I just keep everything else the same, it's true the inequality, because what I did was I replaced this by something more.
Right.
Okay. Now, what I want to do now is, let's look at the terms leading all the way up to 1 over 8. How many do we have up to 1 over 8? 4 terms. And they are all 5, 6, 7 down here. If I replace all of those by 8s, what's going to happen?
It's smaller.
It's going to get smaller again. Why am I replacing those by 8s? Because 1 over 8 plus 1 over 8 plus 1 over 8 plus this one that was already there. What is that equal to? So this is 1/2. How much is this? That's also 1/2. Do you understand this? Now, again, remember, you can take n to be as big as you want because we're taking the limit anyway, okay? So now, from here all the way up to 16, how many numbers do we have? Up to 1 over 16.
8.
How many numbers do we have? 8. So if I replace all of those by a 16, right? I'm gonna be adding 1/16 8 times. That is 1/2. Do you understand what's going on? So now we're gonna have a 1/16, and I'm just gonna be replacing all of those 1/16 until I hit the actual 1/16 that we have in the original sequence to produce another 1/2, because there are 8 of those. Now, how many are from 16 to 32?
616.
So if I replace all of those with 32s, I'm gonna have another 1/2. And because this would be an infinite sum, this is an infinite sum. The point is that I can keep on doing this non-stop. So I'm just gonna have a bunch of 1/2, right? So the reason why I wanted this to be a power of 2 is because that way we can count how many 1/2 we have. So let's see. If I have, let's say that was 2 to the 3, that it stopped at here, how many 1/2 do we have? 1, 2, 3, right? If we would have stopped at 16, if for any 16, we will have 4 1/2, which is 2 to the 4, right? So if I stop at 2 to the n, how many 1/2 we're gonna have? N 1/2, right? N 1/2. So, and so on. So what this is telling me is that if you look at the sequence S2 to the k, okay, so I'm gonna write 2 to the k, let me write 2 to the n. This is gonna be greater than or equal that 1 plus, there are k 1/2, so that will be k over 2, right? K times 1/2. Do you understand this? If n is 8, this is my sequence of partial sums so far. So that's a 2 to the 3. So that's going to be bigger than 1 plus 1/2 times 3. So that's 1 plus 3/2. Yes? If you go all the way up to 16, then there are 4 1/2. So that will be 1 plus 4 times 1/2, which is 4 over 2. Right? So if you keep going, now I'm saying I don't want to stop at 20 or 30 or 1,000. I want this to be 1,024, powers of 2. Just so that I can control it nicely. Okay? Anyways, this is a subsequence of this one. So if this one goes to infinity, this one will go to infinity as well. Do you understand this? This is a subsequence of this one. So, now I know that I'm stopping always at a power of 2, and therefore this right here is going to be greater than or equal to 1 plus k over 2, because there are k 1/2 by playing this game. Okay? Why am I doing this? Because now this sequence is less than or equal than this one. What's the limit of this as k approaches infinity? Infinity. So what's the limit of this? Infinity. It's like the comparison theorem that we did for series, right? If the small one diverges, this one is going to diverge. Therefore, what do we know about this series? It diverges. Okay. Again, we're going to have easier ways of dealing with this once we talk about the integral test. They're going to see that this actually corresponds to the P series of type 1 with n equals 1. This corresponds to 1 over x. The series from 1 to infinity of 1 over x. It behaves the same. And we know that the P series with P equals 1 diverges, so this has to diverge. Okay? For example, just so you can look ahead, if I put a 2 here, this will correspond to a P series 1 over x squared. What do you know about 1 over x squared? It converges because P is bigger than 1. Okay? But that's what's happening in the next section. We're gonna be doing this in the next section. That's called the integral test. Okay, so let's see. It's clear what happened here? Yes? And I should put n here. Okay. So 1 plus n over 2 approaches infinity as n approaches infinity, and hence the limit as n approaches infinity of s2 to the n is also infinity. And since this sequence is just a special subsequence, now I know we didn't talk about subsequences, but it should be clear what this is. If you have a sequence, a subsequence is just another sequence that's made out of some terms of your sequence. Like pick the first guy, now pick the second guy, now pick the fourth guy, then the eighth guy, and so on. That's basically what we're doing. If the subsequence diverges, what do you think we can say about the entire sequence? It's going to diverge as well. Okay. So now the other way around is not true. If the original sequence converges, it doesn't mean that the subsequence will converge. You have to be careful that maybe you will have to sit down and think about it for a second. If the inner sequence gets close to something, then eventually at some point, in all the terms of the sequence, infinitely many are close to that something, in particular your subsequence is close to that something. So yes, actually they go hand in hand, okay? If one converges, the other one will converge as well, or the other way around, okay? So this is a subsequence, and since this is a subsequence of Sn, then Sn diverges. Okay, moral of the story. Therefore, the harmonic series. This is your first example of a divergent series. Diverges. Okay. Do you understand this? So now you take it. You don't have to do this again. We just did this I did this to kind of motivate why it diverges, but we're gonna see other reasons why it diverges, which are easy to understand with this. But you need to know this, that this guy diverges because you're gonna be using this to compare against other series, okay? Because there will be comparison tests in here, okay? And there will be a class of P series, which are related to the P intervals, right? It's gonna be, they will go hand in hand. Okay, we have everything we need to answer the question. So let's now answer the area question. So example number 2. Let's answer the area question. Okay, so what we have is that the area that we are interested in, remember we had the following sequence. So recall, AN is the area of the n square, and the square, we figured out that it had side. What was the side of the square? 1/4 to 1/2 to the n, right? That was the side. It was 1/2 to the n, and then when you do the area, you have to square it, and that's why it became a 1 to the 4, right? But the area, the side of the n squared is 1/2 to the n. So that is 1/2 to the n, 1/2 to the n, by 1/2 to the n. So when you do the area, that's when the 1/4 comes in. Okay. So AN is the area of the n squared of size 1/2 to the n, and this is a sequence. This is a sequence given by 1/4 to the n. So basically, I'm going to list the terms in the sequence. So what are the terms in the sequence? A quarter. So what's the next one? That will be 1/4 squared, which is 116. Then 1/64, right? And then, and so on. The 128, etc. So let me rewrite it as quarter, a quarter square. Let's see, it's more comfortable to write like this. 1/4 to the 4, etc. This sequence is special. Okay, we're gonna take a look back again. Notice that this sequence has the following special property. What happens if I take the first term? How could I obtain the second term? What can you do to the first term to obtain the second term?
You multiply the first term
by 1/4. Good. How can I get the third term if you know the second term?
Multiply the second term by 1/4.
By 1/4. And so on. Notice that this sequence has a special property that if you multiply one term by a quarter, you get the next one. Yes? So when you have these properties, this is called a geometric sequence. Okay? Another way of saying this is that when you look at the ratio of two consecutive terms, you always get the same number. If I divide this guy by the previous one, I will get a quarter. If I divide this by this one, I will get a quarter. Okay? That's called the ratio of the sequence. So let me just say here, note, A1 is equal to a quarter, And if I do 1 over 4 times A1, I get A2. If I do 1 over 4 times A2, I get A3. And so on. In other words, AN plus 1 is going to be equal to 1 over 4 times AN. You understand this? Which is equivalent to say that AN plus 1 over AN equals 1 over 4. And this is true for all n. In other words, AN plus 1 just means the next term, the term after the nth term. Okay? So what this is telling you is that if you take two consecutive terms and you divide them, the biggest one, not in value, but in position. Okay? The biggest one in position divided by the previous one is always a quarter. This is called the ratio of the sequence, and this is called a geometric sequence. Okay? So, sequences like this are called geometric sequence. I mean, it doesn't have to be a quarter. As long as you get a fixed number when you do this, that's called the geometric sequence. Sequences like this are called geometric sequences. And 1 over 4 is called the common ratio. Okay? I'm gonna come back to this later because then, of course, every geometric sequence has a corresponding series called a geometric series. Okay? So basically, what we're gonna analyze now is an example of a geometric series. Okay? All right. So this little fact is gonna help us a lot. Okay? So we want the area, which is basically the sum, right? 1 over 4 plus 1 over 4 squared plus 1 over 4 cubed, etc., which is the sum from 1 to infinity of 1 over 4 to the n. This is called a geometric series. Okay, a geometric series with, okay, let me just say geometric series. We're gonna then have it. From here, we're gonna learn how to deal with geometric series, then we'll do it in general, and then you're gonna have your theorem. Okay, so let's analyze the series. We wanna know what happens to the sum. So what should we look at for this? To analyze the series, what do we need to look at? The limit of what?
The limits.
The limit of what? So to analyze the series, what do you have to look at? I've been talking for an hour.
As the limit of 1/4 to the x, right? So we need it as a function as x approaches infinity.
No, you have to look at the sequence of partial sum.
Oh, right. So
You need to make the series finite and analyze that finite sum. I mean, that's exactly what was written here, right?
Right.
You have to look at the sequence of partial sum. If this sequence converges, then the series converges and it will equal to that number. So we need to direct our attention to this. Okay, sequence of partial sum. All right, so I want to analyze that. I mean, we already know the sequence converges, right? For example, let's get that out of the way. So note is clear. So first of all, note that AN is greater than or equal than 0. Actually, it's greater than 0 for all n, right? Because AN is the area of a little square. So S1 is going to be less than S2, which is less than, okay, let me put Sn. Remember, this is defined to be A1 plus A2 all the way up to AN. So it follows that S1 is going to be less than S2, right? Because S2 is A1 plus A2. S1 is just A1, which is less than S3. In general, we have this inequality. So what that means is that Sn is less than Sn plus 1 for all n. So what does that mean? That the sequence is monotonic, right? It's monotonic increasing. So Sn is monotonic increasing. Okay, is monotonic increasing. Now, if we want to guarantee convergence, what else do we need to figure out? Is it bounded? Is the sequence bounded? The geometry tells us that it's bounded, right? So by construction, so now you can say by construction, we know that Sn, which is the sum of the areas of these finite remaining areas, it cannot be bigger than 1.
Why is it increasing if the numbers are getting small?
What do you mean they're getting smaller? Look at the terms. S2 is bigger than S1. What is S2? S2 is not A2. What's S2? A1 plus A2. What's S3? A1 plus A2 plus A3. So it's very easy to get confused here, and typically students get confused with this. There are two sequences here. There is a sequence AN, which is the one that you use to make your series by adding the terms, and then there is a sequence SN, which is the one that you get by adding the terms of AN, little by little, one at a time. Okay, that's why it's called sequence of partial sums. Okay, and that one, because all the AIs are positive, then whenever you are adding positive terms, you get the property that you get bigger stuff. That's basically what we're going to do. And in fact, in this chapter, we're going to be interested only in series with positive terms, because we get this added benefit that a sequence of partial sum is automatically increasing. We just need to argue that it will be bounded to get our theorems. Okay?
The sequence is always going to be monotonic increasing,
If the terms are positive.
which we're going to do this.
For this chapter. Later, we're going to be dealing why the terms are not positive. Okay? What happens is that sometimes positive, sometimes negative, and then we will try to deal with that case. Okay? So it gets more interesting as we go down the line. But we need to first crawl before we start, trying to walk. Walk. Maybe we will run. We will see if we can run. If we have time. There is a lot of stuff going on here. But whatever we do, I just want you to understand it, because otherwise, what's the point? Okay? Okay, so by construction, we know that Sn cannot go beyond 1 because that's the area of the big square, right? Since 1 is the area of the surrounding. Okay, I may get in trouble here. Did I spell that correctly? Yes.
We know what you are.
Yeah.
Okay. The surrounding square.
You could just put original square? Yep.
Surrounding sounds more fancy, but then it's kind of, or enveloping square.
So basically, for that square, the area approaches to 1 plus, and then that infinite sum.
No. Everything is happening inside this big square. Well, it's not a big square, but everything is happening inside. You see this guy? Everything is happening in here.
Oh, okay, yeah. I see what you mean.
Everything is happening there. So whatever we do, whatever area we come up with, it cannot be more than 1, so it's bounded. Okay. So that sequence is bounded when you add finitely many of those areas. So now we bring the theorem from last time. What do we have here? We have a sequence that's monotonic, increasing, is bounded because it's bounded below by 0, right? It's between 0 and 1. Monotonic, bounded, it must converge. So there is a number to be found. That's the point. So Sn converges to some number A, which A is our area. Okay, but then of course, we are not content with that. We actually want to know what is the area. We know there is an area now. What is it? Okay, so let's find it. So here's what we do. So note Sn. Now we need to take a look at Sn. Okay, so Sn equals 1 over 4 plus 1 over 4 squared plus 1 over 4 cubed, all the way up to 1 over 4 to the n. Yes? That's what Sn is. Now, let's play the following trick. And this is the trick that we use for geometric series. Okay? I'm going to take Sn, I'm going to multiply it by the ratio of the series, which is a quarter. Right? The ratio of that geometric sequence is a quarter. So let's consider 1/4 times Sn. What happens when I do this? What's going to happen to this sum? Basically, I'm multiplying this sum by a quarter. What is that I'm doing? I'm shifting the terms, right? This guy now becomes this one. This one becomes this one, and so on. And then this one gets out of the list and becomes something else, right? So by multiplying this by a quarter, now I'm gonna get this. I'm purposely leaving space. So do you understand this? The first guy, this 1/4 became the next one. This one became the next one, and so on. So this one was from the one before, the 1/4 to the n plus 1, that became 1/4 to the n, and then this last one becomes 1/4 to the n plus 1. Agree? Now I'm going to subtract the two. So subtracting, if we subtract the top minus the bottom, what's going to happen? What do we get on the left?
3/4.
So we get 3/4 Sn. Yes? 1 minus a quarter. And then what happens on the right? All of the in-between terms cancel out, right? The only thing that survives is the first and the last guy. So we get 1/4 minus 1/4 to the n plus 1. So this is one of those lucky cases, because of this special behavior of geometric series, that we actually get a formula for Sn. So we can just take the limit. Now that we have the formula, you can just take the limit. You understand this? So now Sn, to determine convergence, you can just use the formula now and take the limit. So it's going to be 4/3 times this quantity. Okay? And now we take the limit. So the limit as n approaches infinity, we know this limit will exist, but we didn't actually need to argue that. We could have just played this trick and then take the limit and see what happens, because we have a formula. But again, here we are very lucky. This is a very lucky case that we can figure out Sn. And notice that there was nothing, the only special thing that we use about this sequence is the geometric property. So any other sequence with this same behavior, we can play the same game. Understand this? All right. So what is the limit? We go here, right? This is the part that has the n. So what happens to that part? Becomes 0. So what is this limit? 4/3 times 1/4. And what is this? 1/3. Right, so the 4 is cancelled, so we get 1/3. So we gave an answer to the problem. So what's the area? 1/3. So the area equals 1/3. In other words, the sum from 1 to infinity of 1/4 to the n is infinite sum equals 1/3. Questions?
Just in case, have you recorded this lecture today or no?
Yeah, I'm recording.
Okay, just wanted to be sure. I know I stepped out and I missed when you explained harmonic series. I'm gonna go back to it.
I'm recording. Are we okay with this?
Yes.
All right. So, yes.
So this is how we would solve geometric series.
Yeah, now I'm going to write the theorem. Basically, if instead of 1/4 to the n, notice that this was nice because we got 0 here, right? But if we have a number here, and the point is that this is 1/4, I want you to pay attention to this. This guy right here is 1/4 to the n plus 1, right? And so, because this is a number less than 1, when you take the limit as n approaches infinity, you will go to 0, right? But what if this would have been a number bigger than 1? So maybe the sequence that you get the term by multiplying by 2, let's say. So the common ratio is 2. Every time that you move, your terms double. Okay? What's going to happen? So you're going to have here a 2 to the n plus 1, if that was your common ratio. So what will be the limit? Infinity. So it will diverge. So the point is that what we're going to get is the geometric series. If you want to know whether it converges or diverges, you have to look at the ratio of the series. And the theorem is, if the ratio is less than 1, it converges. If it's bigger than 1 or equal to 1, it diverges. Okay? And we actually have a formula what it converges to. When it converges to the first term over 1 minus the ratio. I'm going to write that down immediately. That's the theorem. So you don't have to do, we're going to do this one more time in general for any geometric series, and we're going to come up with a formula. And then you need to know the formula because geometric series are going to pop up everywhere. Okay? And you need to know how to find the sum of a convergent geometric series. The formula is pretty easy. For example, this 1 over 3 can be computed as follows. The first term of the series, what's the first term of the series? 1 4 over 1 minus, what's the ratio?
1 4.
1 4. Now we calculate, what do we get? I mean, the easier thing is to multiply top and bottom by 4. So you get 1 over 4 minus 1, which is 1 over 3. Okay? So as a formula, first term over 1 minus the ratio. Okay? We're going to figure that out immediately now. Okay. All right. So in fact, that is the point. So for now, there are 2 types of series that we're going to be able to compute exactly a sum. One is geometric series because we're going to have a nice theorem that will tell us what to do, and then the other type of series that we can compute the sum is a telescopic series. Okay, and we're going to see what they are. But then, other than those 2, most of the time we're just going to be trying to determine whether it converges or diverges. But then that's it, because it's actually pretty hard. This was a lucky case to be able to come up with a formula for the sign. That's not an easy process. This one is because the sequence is super nice. It's a geometric sequence. Okay, so we now have all the tools for geometric series. So again, what's the definition of a geometric series? So let AN be a geometric sequence. So we already defined geometric sequence before with ratio R. So in other words, what does this mean? This means that if I do AN plus 1 over AN, what is this equal to? When I take the ratio of 2 consecutive terms, I always get the same number. And we call it R. In our example, it was 1/4. Okay? In other words, this is equivalent to say that to get AN plus 1, all you do is R times AN. So to get the next term, just look at the previous one and multiply it by this common number, this number that we call it R. That was our 1/4 in the example before. Okay? So because of this relation, this recursive relation, we can actually figure out a general formula for AN. So let A1 be equal to A, be the first term, then what will be A2? It will be A times R, right? What will be A3?
A times R squared.
A times R squared, very good. And we keep going this way, what will be AN?
A times Rn.
A times R to the n minus 1. So notice that this is R to the 1. So you have a 2 here, here's a 1. You have a 3 here, it's a 2. So it's always one step behind, right? It will be A times R to the n. It will begin with 0. If the first term, if the index is 0, that's why sometimes we like to begin with 0, because that way then, instead of the formula looking like this, it will look like A times R to the n. If you start with 0, okay? But if we start with a 1, this is how the formula looks. The point is that a geometric sequence can always be written in this form. The general term of the sequence, the AN term, can be written as a number times R to some power. And that power is the one that is increasing as the counter increases. That's the form, okay? I guess, let me say here, if n starts at 0, then A0 would be equal to A, A1 would be A times R, and going this way, then our AN would be A times R to the n, okay? It really depends where we start, okay? So, definition. The series an is called geometric if an can be written in that form. Okay, it's called geometric with ratio r. With ratio r, if an equals a times r to the n minus 1, or a times r to the n. You know, it really depends whether we started at 0 or at 1 or at 0. Okay. Okay, like this, with a being the first term. Okay, so bottom line, a geometric series is a series that has a form something times r to the n minus 1, or the sum from 0 to infinity, and then it will be something times r to the n. Okay? Look at. So this is how geometric series look like, and we can analyze them. So theorem, actually, note. I'm gonna just work with the red one, okay? But whatever we do for the red is the same as what we do for the blue, okay? So Sn is gonna be a1, is gonna be a times r, no, is a plus a times r plus a times r squared, all the way up to a times r to the n minus 1, okay? That's Sn, the sum of the first n terms, okay? Then if you multiply everything by r, if you multiply Sn by r, what do we get? The shifting of the terms, right? So we get ar squared, and then this last term becomes a times r to the n, right? Playing exactly the same trick. Subtracting, what do we get? We get factor out an Sn, so you get a 1 minus r, yes? Equal to, then all of the in-between terms are gone. So we get the first guy minus the last guy from the bottom row. And so we have our closed formula. This is the formula of the sum of the first n terms of the geometric sequence, okay? A minus a times r to the n over 1 minus r. In other words, typically we like to factor out the a. So this is 1 minus r to the n over 1 minus r. And then if you want to analyze, notice that this is for any geometric sequence, okay? It doesn't matter what a and r are, okay? So this is for any. And then if we want to analyze that series, we just have to take the limit of this formula. And as you know, this limit depends entirely on r. If r is greater than or equal than 1, this limit is going to diverge. So this is diverges. If r is less than 1 in absolute value, then this converges. Okay? So the limit as n approaches infinity. If you use the 0, 1, then you have an n plus 1 in here. Okay?
Wait, can you say that last part again? It's you said that if you do with a starting at 0,
you will have an n plus 1 instead of an n here. Because you know the last guy here will be to the n, and then you multiply the last one here will have n plus 1.
right? Yeah.
But you know the idea is exactly the same. So if we do the limit as n approaches infinity, that's going to be the limit as n approaches infinity of this. And then let's see. If the absolute value of r is bigger than 1, then what happens to this limit? Because this is a number in absolute value that's bigger than 1, then when you raise it to the n power, this part is going to go to positive infinity or negative infinity, depending if r is positive or negative, right? So because you have a base that's bigger than 1, okay? So if that happens, then diverges, because it's going to go to positive or negative infinity, depending on whether r is positive or negative. And if r is less than 1 in absolute value, it could be like negative 0.5, okay? So if r is less than 1, then this converges. And moreover, when r is less than 1 in absolute value, this is going to go to 0. So this limit will be a over 1 minus r, which is a formula. And let's see, what happens if we make it equal to 1? So first of all, if r is equal to 1, we cannot play this game because we're going to be dividing by 0. But if r is equal to 1, all you're doing is, in this sum, just adding a infinitely many times. A plus a plus a plus a plus a non-stop. Divergence, right? Now, if r is equal to -1, what's happening? If r is equal to -1, then this sequence right here is going to be what?
0.
No, because sometimes it's 0. It's going to be alternating. It will be 0 or 2 times the sig. When n is even, it will be 0. When n is odd, they're going to have a 2 over 2, so it will be 8. So the sequence will be 0, 8, 0, 8, 0, 8, 0, 8. So it doesn't converge. Right? It's like the 1, 3, 1, 3, 1, 3 that we were looking at before. Understand what I'm saying? So when r equals 1 or -1, it also diverges. Therefore, we can improve this and say, if the absolute value of r is greater than or equal to 1, this is going to diverge. Only when it's strictly less than 1, it converges, and we know what it converges to. Okay? So that's our theorem. So theorem for a geometric series with the ratio r and first term a, we have the following. So in other words, we're talking about the sum from 1 to infinity of a times r to the n minus 1, or perhaps the sum from 0 to infinity of a times r to the n. Doesn't matter, it's exactly the same thing, okay? So for this type of series, then we have, so for the series, we have r and first term a, we have that number 1, if the absolute value of r is less than 1, then it converges. And moreover, the sum equals a times 1 minus r, where a is the first term. This is very important. It's the first term. And number 2, if the absolute value of r is greater than or equal to 1, then it diverges. So now, once you see a geometric series, you can just look at it and you can tell whether it converges or not. R will tell you. Okay? And if you want to know what it converges to, just use the formula. That's all it is to it. I'm just going to write one example. What do you think about this series? 1 over 2 to the n. Converges or diverges? So you can write this as, so now, exactly. So now you have to learn how to manipulate. So as we do examples, you will see the type of manipulations that we do. Remember, to recognize this as geometric, you need to have it as something times something to the n. Here, my first term, if you want to know what a is, to be technical, if you want to know what a is, you can rewrite this as, take out 1/2, and then this will be an n minus 1, right? Now you can see that your a is 1/2 and your r is 1/2. But you could also say that r is 1/2 and then there is a 1 in here. Because I remember a stands for the first term. What's the first term? 1/2 anyways. Just if you wanted to fit that form that we have above, you have to play this little trick. Okay? So you can immediately see that this is geometric. So this is geometric with first term equals 1/2 and ratio 1/2 is less than 1, so converges. Okay? Let me say absolute value of r equals 1/2, which is less than 1, so converges. Now, if you want to know what it converges to, what is it? 1/2 or 1 minus 1/2. So what is this? 1. So there you go. That's a fancy way of writing the number 1. 1/2 plus a quarter plus an 8 plus a 16, etc., etc., etc. That equals to 1. So now you can show up. All right. Do you understand this? Okay. So next time, try to see if you can do this on your own for Tuesday. So I'm gonna leave this as a homework. How about this one? This is not geometric. Let's see if you can analyze this guy. Okay? This is what we call a telescoping series. Just write down a sen and try to see if you notice something interesting. Notice that what's going to happen is that a bunch of the in-between terms, a bunch of terms are going to cancel each other. Because the first term is 1 minus 1/2. That's the first term of this series. Yes? What's the second term? 1/2 minus a third. So the negative 1/2 from here cancel with the 1/2 from here.
Right.
Then what's the other one? A third minus a quarter. So the negative third from here cancel with the third from here positive. And this is gonna keep happening.
Until we find our
But the first guy is gonna survive here, and the last guy is gonna survive here. So the finite sum will actually be 1 over n plus 1. 1 minus 1 over n plus 1. Then you take the limit, and the limit is gonna be 1. So this is what we call a telescoping behavior, that you get this cancellation. Now sometimes this one is straightforward, but sometimes it happens that you don't get cancellation, and then eventually this guy cancels with the third guy down the line. And then the next, you have to learn how to spot that. So we're gonna do examples with that. So telescoping this is a nice case of telescoping. Telescoping just means that there are these cancellations and only finitely many survive. So that's what we're gonna be looking at next time. Okay. All right.